Thank you. Hi, everyone. I'm Pratyush, and I'm presenting Oblix, which is an efficient, oblivious search index. This is joint work with Rishabh, Jerry, Alessandro, and Raluca at Berkeley. OK. So today's search indices are used for all kinds of applications. The normal architecture for this is that you have a client who outsources the index to some remote server so that they can later make queries and get back the result. However, these indices are often used to store sensitive data, and if the server becomes compromised, then the attacker can learn not only the contents of the index, but also the queries that the client is making. So over the past 20 years, there's been a lot of work on performing search over encrypted data. And the general architecture or paradigm of these works is that the client has a secret key. They use this to encrypt the index before uploading it to the server, and they can make later encrypted queries and get back encrypted results. However, one problem with almost all efficient solutions in this space is that they leak access patterns. What are access patterns? Well, basically, they leak to the adversary which location in the index is accessed in response to a query. So for example, if I make the same query twice, then the adversary sees that the same location in the index is accessed twice, and then infers that the same query was made. This is without breaking the encryption scheme in any way. A bunch of works of the past 5 years have used this leakage to recover not only query contents, but also the contents of the index. OK. So one potential solution for this is to use Oblivious RAM. Oblivious RAM basically allows you to make these encrypted queries without revealing to the adversary which location was accessed. It looks as if you were accessing a random item. The natural question now is whether we can use Oblivious RAM to get secure search indices. But we immediately run into some problems. The first is that even the most efficient state-of-the-art schemes today require a number of rounds of interaction and have a high bandwidth overhead. The second issue is that ORAM is in some sense inherently single user. The client has a single key, and they don't really want to share this with other users because they might not trust them. For example, if you use ORAM in a big web app where anybody can sign up as a user. OK. So what we do in Oblix is construct an efficient oblivious index that is low latency, has low bandwidth, supports multiple users, and also supports inserts and deletes. We achieve this by a combination of hardware enclaves as well as new oblivious algorithms that leverage the enclaves as well as fix their shortcomings. OK. So let's quickly recap what hardware enclaves do. They basically allow a user to outsource execution of their program to some possibly malicious remote server in such a way that the adversary doesn't learn information about the program execution. So in more detail, the user is able to establish some secure channel with the enclave, and they can then send the program and data over this channel. The enclave runs the program and sends back the result. The guarantee that these enclaves claim to provide is that the attacker only sees encrypted data. And this is achieved by having all the information touched by the program be encrypted by a secret key that lives in the enclave. So this seems too good to be true, right? This solves all the cryptographic problems that we've faced over the past 30 years. And indeed, modern enclaves have a drawback. They all suffer from some kind of side channel leakage. One in particular that's problematic for us is that enclaves leak memory access patterns. What this means is that when the running program accesses some location in memory, the adversary can see which locations are accessed. It can't see the contents of the memory, but it does know which locations are accessed. And a bunch of works over the past 3 years have exploited this leakage to recover the secrets of the running program. OK. So let's put aside for a moment this leakage and see how we can use these enclaves to solve the problems with ORAM we saw earlier. Our key idea is to just run the ORAM client inside an enclave. So now in this setup, there's the ORAM client running in an enclave at the server. And when a user makes a query, the client interacts with the index that's living in server memory and sends back the result to the user. This solves our problems earlier because, for example, we get low latency and bandwidth because now there's no interaction at all occurring over the network. All interaction is between the enclave and the server's memory. We also get easy support for multiple users because now all the different users can interact with just one enclave, which can enforce the relevant access control policies without having to store any secret state at any of the users. OK. But here's where the side channel leakage comes back to bite us. ORAM is formulated in a model where the ORAM client lives at the user's device, and the adversary can't see the inner workings of this device. However, what we've done now is taken the client and put it in an enclave, and the adversary can observe the internal accesses of the client to its internal data structures. To see how this is a problem, let's look at a concrete ORAM protocol, namely path ORAM. So in path ORAM, items are arranged in buckets, and these buckets themselves are arranged in the form of a binary tree. Sorry. And each item is associated with a path in the binary tree and lives in one of the buckets along this path. Oops. So this, ignore that for a second. This mapping between items to path is called a position map, and usually it lives inside the ORAM client. But there are various techniques, such as recursion or oblivious data structures, that allow one to get rid of the position map without having to worry about, it. So how path, the data structure that we do worry about is called the stash, and this temporarily holds items between accesses. So how path ORAM achieves obliviousness is by enforcing that whenever I read an item, I have to assign it to a new, different, uniformly random path. This ensures that now when I make an access for the same item twice, I'm accessing independent paths, and the adversary can't make any correlations. OK, so let's see how you can actually read and write items in path ORAM. So let's say we found out that the item that we want lives on path 2. What we do is we fetch path 2 and add it to the stash. This is a data-dependent process because the locations in the stash that we access depend on the contents of the path as well as the item that we're looking at. So this is data dependent, and this gets even worse because now we have to look in the stash to find the item that we want to return to the user. So writes are data dependent. Reads are data dependent. What about writes? In writes, we basically conduct this process in reverse. We look in the stash and try to construct buckets for the path that we're writing back. This is again data dependent. Okay, so what we want is W-oblivious algorithms, and this is the notion that we introduce. This roughly means that whatever internal accesses the ORAM client makes to its internal data structures are data independent. In our case, the memory or the data structures live within the enclave. Okay, so here's a roadmap of how Oblix constructs and builds upon W-oblivious algorithms. First, we construct W-oblivious path ORAM or path DORAM. Next, on top of this, we construct W-oblivious data structures to get rid of the position map. And finally, we construct Oblix by constructing a doubly-oblivious index on top of this. In the rest of this talk, I'm going to focus on path DORAM. For the other two, I recommend you look at the paper. Okay. So let's see how we can make path ORAM oblivious or W-oblivious. The simplest way to do this is to make all stash accesses linear scans. These inherently become data independent now. However, this is lacking in terms of performance. If you have n items, then path ORAM says the stash size is log n, and then the complexity of a single access, particularly the write, becomes the stash size times the path length, and this is quadratic in the stash size, or O of log squared n. We improve upon this by making a key observation. The idea is that when you read a path, you get not only the item that you wanted, but also these other items that are irrelevant to your query. Furthermore, you're only really reassigning the single item that you requested. All the other items already live in the correct buckets, so we don't need to reassign them. We take advantage of this by splitting the stash into two parts. The first, called blocks, holds only those items that we specifically requested, not the extraneous ones. Whereas buckets holds these extraneous items. And the key observation is that the size of buckets is much greater than the size of blocks. The size of buckets is log n, which is the size of the path, whereas blocks consists of one or two items that you specifically requested. So let's see how you can perform a read in this new architecture. As before, we get the path from the server, but before we insert it into our stash, we scan the path and replace the item that we wanted with a dummy item. This is data independent because we're doing this via linear scan. Next, we take this explicitly requested item and add it to blocks, again via linear scan. So this is again data dependent. Next, we add this modified path to buckets, But this step doesn't have to be done in a data-independent manner because the adversary knows exactly which buckets we requested. Finally, to return the item to the user, we scan blocks again and return the item. This is, again, data-independent. OK, so this is good. We've made reads data-independent. What about write-backs? So the idea is not too complex. What we do is, for each item in blocks, we scan the path that we're writing back and figure out which bucket the block can fit in. This gives us a time complexity of size of blocks times size of buckets, which is much better than the naive version, which has complexity size of buckets squared. And this is also data independent. OK, so now we're good. We've made reads and writes data independent. But let's see if we can improve the performance more. And how we do this is by getting rid of linear scans inside writebacks. Instead, we use cleverly designed oblivious sorts, which ensure that the items in blocks go into the relevant empty slots efficiently. So let's see how this improves our runtime. So if you have a stash size S, then the naive algorithm has, as I said, runtime quadratic in S over S squared. But Oblix takes time S log squared S, which is just quasi-linear. And this is reflected in our evaluation. So we implemented and evaluated this, where we see that for a single read plus write, when the ORAM is operating in recursive mode, takes 2 milliseconds for naive, but only 0.5 milliseconds for Oblix. Furthermore, we also designed a new algorithm for initializing the index for loading data into it, because the naive method of just performing a read plus write for every item that we want to insert is way too slow. It takes over 10 minutes for even small, like 65,000 items. And since our experiments, we wanted to evaluate Oblix on millions of items, this would just have been infeasible. So we designed a new algorithm that takes only 2 seconds to perform this initialization. And this, yeah, so we have the gap grows even further as the number of items we insert increases. OK. So now we've discussed Oblix. In our paper, we also evaluated Oblix on 3 applications. And in the rest of the talk, I'm going to talk about one specific one, namely signal contact discovery. OK. So Signal is a secure messaging app. And when users sign up for Signal, they have to discover which of their contacts are also Signal users. Currently, how Signal does this is by having the users upload their contact list to an enclave on their servers. The enclave then, for each contact in the user's list, scans the list of Signal users and finds the intersection and sends it back to the client, or to the new user. This is linear in the runtime of the database, in the size of the database, as well as the size of the contact list. Since Oblix has better performance, it only takes logarithmic in the size of the user's database, in the size of the Signal user database, we decided to perform this search using Oblix and evaluate how long it takes. What we found is that for an initial sign-up, Signal's approach is already slower than Oblix's approach for only 80 million users. Even better, in the steady state case of when a user has already signed up and they're only adding a new contact to their list, our approach, Oblix, is already better than Signal's approach for just 500,000 users. And this gap only grows as more users join the system. OK. Yeah, so in conclusion, I presented Oblix, which is an efficient oblivious search index. And we demonstrated its application to we applied it to 3 applications. All right, thank you.
We have some time for a few questions. Any questions from the audience? Well, I can start with a question. Do you want to take this opportunity to compare? Okay. Do you want to take the opportunity to compare a little bit with Zero Trace, which was a paper published in NDSS 2018? Yeah,
so NDSS also has a W-oblivious path ORAM. They don't call it as such, but they employ the linear scan strategy, the naive version that I introduced in the talk. So their performance is O of S squared on the stash size. And actually, the numbers that I compared against in the evaluation for Oblix are against zero trace. And so they also implemented circuit ORAM, but we found that our implementation of W-oblivious RAM was already faster than circuit ORAM as well.
Okay, thank you.
Yeah.
Hello. Hello, this is Attila Yavuz from Oregon State University. So very nice talk.
Thank you.
Actually, I was about to ask same circuit ORAM question. So do you think your strategy can be extended to circuit ORAM to even improve the benefits of what you have done with path ORAM?
Yeah, certainly possible. One thing to keep in mind is that circuit ORAM was formulated in a model for MPC, where the cost of computation is much higher than the cost of communication. So what circuit ORAM does is you have, I think, 2 IOs per logical access. But in our model, where we're running in an enclave, computation is like super cheap. It's just native execution, so the cost of IO goes up relatively. So it's certainly possible that we could apply techniques to circuit ORAM as well, but I'm not sure if the performance would improve. And when we compared it against zero trace, which does implement circuit ORAM, we found that our approach was still faster than the circuit ORAM that they implemented.
Okay. And one last question is, so you are also using a multi-user model with access control.
Yeah.
So what kind of access control data structure you have used, and how did you throw an ORAM on that access control data structure? Because I don't know if you store your access control data structure in enclave or outside of enclave, and if it is outside of enclave, how did you handle ORAM on that?
No, so we just enforce access controls inside the enclave. The enclave is responsible for the access control policies. You just write your native code and execute it inside the enclave.
I see.
We don't have additional cryptography on top. It might be possible to layer it, but we didn't consider it in this work.
I see. Okay, thank you.
Thank you.
Kapil Vaswani, Microsoft Research. A quick question about the overheads. Where's the bottleneck? Have you compared the W-oblivious with the oblivious one? Is the bottleneck in the scanning you are introducing, or is it in the path ORAM already?
So there's 2 overheads. The first, path ORAM introduces its own overhead because you're reading these additional items. And you also have, you can't really get high throughput because there's not much concurrency inherent in path ORAM. So there's one there. But compared to path ORAM, our system is also a bit slower because we have this, we can't make data-dependent accesses within the enclave. But that overhead is negligible compared to the cost of path ORAM itself. Yeah, thank you.
Okay, let's thank Pratyush again. Thank you.
Thank you.